Good afternoon, everyone. So this week we don't have lab because of fall break. Also, I have quiz 2 is posted on Dropbox, and it's due on Friday at 11:59. There's only 7 questions, and I apologize for not getting that out sooner. I also posted Lab 3. Here we have the skeleton posted and the description. There's a good chance that Charles will make some changes to this as he refines it. But in a nutshell, the objective of this lab is to design the first version of the RISC-V CPU. You'll notice that going from Lab 2 to Lab 3, there's a big jump in difficulty. Mostly because we don't know how else to do it. Basically, we're going to have you design a CPU that implements just a few of the RISC-V instructions, but it is going to require you to put a bunch of stuff together in System Verilog. So the due date for this is the end of this month, October 31st. So you have some time, and the TAs will also be helping you out in lab, obviously. Now you'll notice that the lab description here is 19 pages long, and the reason for that is there's a lot of reference information in here. And over the years, this description has grown quite a bit. I think most of it, though, is the encodings for all of the instructions that you'll be building into your CPU or supporting with your CPU. So you can use the lab sheet as a reference for that. The TAs are going to do demos this year, so we've experimented with different ways to do grading on this in the past. We've tried to automate the grading of it, but it was really difficult. There was a lot of issues we ran into. So in addition to building your CPU, you're going to be writing a program that will take the switch input values from the board and convert them from binary to decimal with a short MIPS program that just runs in an infinite loop, and then displays, RISC-V program that runs in an infinite loop and will display the output to the hex displays. So you'll be reusing your hex decoder that you developed in Lab 2, and you'll have to write a short MIPS program in addition to, RISC-V, in addition to designing your CPU. Okay? As far as I know, Lab 2 went pretty well. Any issues? I haven't heard any problems. Okay, good. Okay, great. Okay, so we're jumping back to RISC-V. And one thing, the last thing I covered last week was memory in using an always statement in System Verilog. And I wanted to demo that, and I didn't get a chance, so I think today is a good time to do that. So for example, we can build a register, but don't get yes?
Yeah, one question before we start. What about midterm? When do you plan to do it?
Oh, the midterm, yeah, I told you I would make a decision on that. I'm going to do it online. So the only issue with that is, since it'll be online, you can take it, outside of class. If I had given it in class, then we would take a whole class period to take it, right? So I think the only issue I have with the online version is that, do I cancel a class? Because otherwise, we wouldn't. If we took it in person, we would have a class essentially taken up by the midterm. So I hate to do that, but I think I'll probably end up doing that unless someone strongly objects to that. And so, basically you could use that time that you would normally be in here to take the midterm. Okay, and that'll be on October 22nd, right? Yes?
Sorry if you already mentioned this, but do we have a quiz this week?
Do we have I'm sorry?
A quiz this week?
Yes, there's a quiz. Yeah, quiz 2 is posted. It's on Dropbox. You have all week to take it. So I think there's 7 questions, 2 attempts. It just covers essentially the always statement. Yes?
So we'll take the midterm during class time?
Yeah. Yeah, and you won't have to. You can take it, generally I'll open it for the whole week, but once you start taking it, you'll have 75 minutes to finish it. So you won't have to take it during class. Okay, so I mentioned that in your CPU you're going to have registers, but there's two types of registers. There's this type of register which basically delays it captures a value across one or more cycles. Oftentimes it's just used to delay a value by a cycle. And you can think of that as just a multi-bit flip-flop. Then there's the architectural registers, the RISC-V registers that you can address in your program, in your software. And those are actually addresses in a RAM. So today I'm going to start out by talking about the difference between how to build registers and how to build RAMs. Okay? So this is a register. You can implement it with as little as essentially one always statement with one statement inside of it. So this says always underscore FF at pos edge clock. So this is a positive rising edge active flip-flop or register. And it also has a synchronous reset because the reset is not part of the sensitivity list. So this thing doesn't do anything except for on the rising edge of the clock, at which point it could be reset if reset happens to be high at that time. Or you can, if the write enable is high, it will capture D into Q and hold it, right? And in this case, the width, you wouldn't really know what the width is from the code of the flip-flop, except for in the reset, you can see the reset value specifies 4 bits. But if you didn't have that, then the width would be sort of implicit depending on how you declared Q and D, which you can see up here, they're declared as 4-bit signals. Yes?
Did you enable signal instead of VE signal? Else if and then Q assign D.
Else if, well, this is write enable, WE.
Just mentioned in
Oh, I didn't. Oh, you're right. Yeah, it's EN here. Yeah, you're right. that's a good catch. Yeah, I wonder how that happened. Yeah, that should be EN. Well, EN enable, write enable. You decide on one of the two. I'll just change it to EN. Yeah, that's a good catch. Okay, now so let's let me show you an example of this. Now you may already be comfortable with this from your experience writing the test bench, but just in case any of you are not, or you're not entirely comfortable with this, I'll do a quick demo here. So let's create a directory. I'll just create something called top.sv. So module top end module, and then shift width equals 4. Okay, so let's declare a. Let's make it 7 down to 0. So we'll have an 8-bit signal called A, and 8-bit signal called B, and an 8-bit signal called C. Then we'll have a single bit clock, and then I'm going to do something you don't normally do, but I'm going to just generate the clock right here. So I'm kind of mixing up the test, would normally be in the test bench and the design under test. I'm just going to put it all into one module. So always begin clock equals, say, 0, delay for 5, clock equals 1, delay for 5, end. Now, in this case, it's important that hopefully you guys can read that. There we go. That's a little better. That's too much. Maybe not. There we go. Okay, so yeah, there's 4 statements in there, so I need the begin and end. And then I'll add a always at pos edge clock begin end, and I'll just say B is going to get A, and C is going to get B. And so I need something for A here. So I'm going to do a thing where I'm going to generate A, but I'm going to generate kind of a random sequence of values. I'm going to use a linear feedback shift register. So I'm going to say the new value of A after on the rising edge of the clock is going to be A, let's say bit, I don't know, 4, and I'm going to do an XOR with A bit 0, and then I'm going to concatenate that with A bits 7 down to 1. So this will create a random sequence for A. I have to initialize A though, so I'm going to initialize it here when I declare it, and I'll set it up to be 0, 1, 0, 1, 0, 1, 0, 1. Okay? All right, so hopefully that works. So what should be happening here? Well, A is going to get a new value or a new state every rising edge of the clock, and then B and C are going to be old values of A. B is going to be what A was in the last cycle, and C will be what A was 2 cycles ago. You guys see that? Okay, so vlog top.sv. Okay, no errors. So I'm going to do vsim top. Push it in the background. Okay, so model sim comes up, and I'm just going to do a right click on top and say add to wave. That'll add everything, and then I want to put everything here in hexadecimal, and then run it. Hopefully I did the. Okay, wow, that's okay. So you can see if I zoom in here just a bit more, you can see that so the value of A starts out as 5, 5, which is the hex version of 0, 1, 0, 1, 0, 1, 0, 1. And then it changes to 2A, 1, 5, 0A, 0, 5, 8, 2, 4, 1, A0, 5, 0, A8. So this random sequence of values is from that linear feedback shift register. And then B, you can see B is one cycle lagging A. You see that? So A is so A is 0A there, it's 0A there, 0A there, right? And these things are changing on the rising edge of the clock. You can also see that B and C are undefined at the beginning initially, because I don't give initial values for them. So I don't know what B is until the first rising clock edge, and I don't know what C is until the second rising clock edge. You guys see that? Now, the reason this is important is because this is how you're going to implement your pipeline registers in your CPU. Your CPU is going to be pipelined, and hopefully you learned about that in 2.12. You're going to have instructions moving through the CPU in a pipeline fashion, and you're going to have pipeline registers. And so at any moment in time, like for example, if I click that moment in time there, you can see the value.
Previous stages.
Right, of all 3 stages, yeah. Yeah, exactly. Does that make sense? Okay, so those are registers, and then there's RAMs. Now the difference between a register and a RAM is that a RAM has an address. So you could think of a RAM as an array of registers, or a 2D array of bits. So for example, you can have a 1024 word by 32-bit array. And the notation here, it uses the same format that you use in Java or C++ or in linear algebra. Yes?
Shouldn't people memory arrays also has inputs, input to which is read or write request? Like 10 bits?
They can, yeah, they can. In this case, this is a simple one where I'm just assuming that it's going to read every cycle, or it's always constantly reading. Actually, there's not even a clock here, so it's unclear if there's a clock even involved here,
Which
right?
edge of the clock?
But this is just a simplistic version where there's essentially one port, right? So I have one address. So now the notation here is the first value, the 1024, is the number of entries or the number of unique addresses, you could I think of it as the number of rows, right? The depth, the height, right? And then the second number is the width. Now remember, I mentioned last week that when you declare a RAM in System Verilog, you have to declare them backwards. It's the width and then the height, which I don't know why they did it that way, but generally whenever you see a RAM array, it's going to be height first, then width, right? Okay, so the height or the depth is corresponding to the address. So the address is going to be the log base 2 of whatever the depth is. So if it's 1024 word, then there's 10 bits of address, right? It's log base 2 of 1024. And then the width is the number of bits you're reading out or able to write in parallel, 32 bits. So that's the second number, that's the width, okay? So, let's see, yeah, I just explained all that actually. Okay, so let's take a look at an example of that. Here's another example. Now the depth is, as you might imagine, the depth is usually a power of 2. It doesn't have to be, but generally it's going to be a power of 2. Now you can declare a RAM in System Verilog and then synthesize that to an FPGA, which means it'll be a RAM, it'll be an on-chip RAM, right? But this is fundamentally the same way that like a DRAM works, off-chip, right? So there's different memory technology. Of course, there's flash RAM and there's all kinds of memory technologies, but they all sort of can be, their behavior all sort of matches this, this pattern, okay? So let's take a look at a RAM array here. So I'm gonna go back up here and I'm gonna declare a RAM array. So as I mentioned, you just say logic, let's say it's 8 bits wide. Okay, so again, the width comes first, which is dumb, but that's how they do it. And then the name, RAM, I'll just call it, it doesn't have to be called RAM, I'll just call it RAM. And then the depth. So the depth, let's see, let's do 15 down to 0. I'll just make it 16 entries deep and 8 bits wide. And then down here in this this always, I can put a statement in like, let's see, out val gets RAM of A. Of course, A is 8 bits, so I'm going to say A 3 down to 0. So I'll take the low order 4 bits of A. You might say, why is the address 4 bits? It's because the depth was 16, and the log base 2 of 16 is 4. So I'll take the low order 4 bits of A, and I'll plug those into, and I'll read that. Now, because I've got that on the right-hand side of the assignment, that's implementing a read port into that RAM, and then I can also write into it as well. So I can create a RAM of A of 3:0 equals, I don't know, A. And then out val is something I have to declare. So logic 7 down to 0, out val. All right. Okay. All right, so I'm going to vlog top.sv, no errors, and just go back over here to model sim and restart. And when I restart, I should see out val listed here, so I'm going to add that to the wave. And notice, wait, what's address? Did I add address? No, okay. Okay, so back to model sim here. Oh, that's interesting. Okay, and then RAM. I'm gonna add this to the wave as well. Now the RAM is a 2D array now. So if you hit, like normally if you hit plus sign here on A, it just shows the 8 bits, right? But if I hit the plus sign on RAM, it's going to show me the 16 entries, as well as I can expand any one of those entries out, into its individual bits. So if I go over here back to the wave, what happened to my other stuff? I guess it cleared the other stuff. Okay, I'm just going to add everything and go back to wave. And I'm going to delete out val because it's already re-added that. Now you'll notice that one of the annoying things is in model sim is when you when you do a right click on like a level of the hierarchy and you say add to wave, you want to add everything in there, it won't add memories, RAMs. I don't know why. You have to add those individually for whatever reason. But I did that, so I've got RAM in here and I got all the stuff. So now I'm going to go ahead and run that a bit. And in order to see what's happening here, I'm going to hit the little expansion thing here on the RAM, and I'm going to convert all of these guys to hex. Radix, hexadecimal, and okay. So you'll see what's happening here is you'll see that, that I've got a random address, right? And I'm writing every cycle, and I'm writing to a random location every cycle, right? So you can see, the first value I write is 5, which makes sense because remember A started out as 5, 5, and I'm writing to the low order 4 bits. And then I write to entry 10 because, let's see, hold on, let me convert all these guys to hex too. Radix, hexadecimal. So there's 5, 10, 5, 10 again, you can see, so this 10 gets written multiple times, which is why it doesn't seem like anything's going on between these 2 points, right? And, and the value I'm writing in there is, yes? Yeah, it's, let's see, how can I fix this? Let's go to View, Virtual Screen. I'm going to scale this. Actually, you know what? Let me just do it this way, if it lets me. There we go. It's a little pixelated, though. Is that a little better?
Yeah.
Okay. Okay, so let's take a closer look. What's going on there? So, for example, if I look at one of my clock edges here, like right there, I got a rising clock, and A is F, so at that point I should be writing to 15, address 15, which I do, right? AB. Now, why am I putting AB in there? That's a question. So let me zoom back out here a bit. Back to the code here. Okay, so so I'm putting A into there. Oh, that's interesting. Okay, so it's putting AB in there. So RAM is 8 bits wide. A is 8 bits wide. A is the address. And it is putting in, it should be putting in the address, the full address, as opposed to just the low order, 4 bits of A, rather, or the full value of A, rather, as opposed to the address, which is the lower 4 bits of A. But it's putting in AB. That's interesting. I actually don't know why it's doing that. What am I missing here? So we have the correct sequence, right? So A, again, if we look at so we've got F, so of course on this rising edge I'm writing to 15. On this rising edge I'm going to be writing to 15 again. On this rising edge I'm going to write to 7, which is this guy down here, which is 7. So we get, so the values that I'm writing are correct. The only thing that's strange about it is the value that I'm actually writing is AB. I must have a typo in there somewhere. So AB. And if we look at A, oh, that's what I was looking at, actually, right when I was getting the address. Yeah, A is, there's A. Let's look at these as, let's view these as binary. Radix binary. Yeah, it is a B. That's right. Interesting.
What signal we're looking at? Is it output or RAM? Output or RAM?
Well, right now I'm just looking at the output, and that's a good point. So let's look at the out val here as well. I'm actually looking inside the RAM. So the reason I wanted to show you this is this is a common way to debug your CPU, because when you run your code, what you're looking for is the correct values being written into the registers. So you're going to have a register file, which is a RAM. It's going to be a 32 by 32 RAM, so it'll be 32 deep as well as 32 wide, and that represents the the RISC-V registers. Then you'll write your RISC-V program, and your program is going to, most of the instructions write a register, right? And so when you look at your program, you can imagine what the values that it's supposed to be writing in there are supposed to be. And so to debug your hardware, where I usually start anyway, is at least once you have most of the CPU put together, is I just start with expanding out your register file and looking at the sequence of writes to the registers. So this is how you would do it. So the out val is on there as well. So you'll notice that the out val spends a lot of time just read, right? Now I know the reason for that is because this RAM has a synchronous read. So RAMs are, whenever you have a write, whenever you're writing to a RAM, that's always synchronous, right? You write on the clock edge. That way you know that your writes are controlled. They're only happening on the rising edge of the clock. However, the reads don't necessarily have to be on the clock. You don't have to have the read line of code inside this always. You could take it out, and you can control the reading outside of the clocked logic, the block that's inside that always at pause edge clock, right? And in fact, your register file will be using an asynchronous read, right? Which we can change that really easily. All we have to do is take that line of code out. So I'm going to delete that, and then stick it outside of the always, and then of course I have to put an assign in front of it and take the non-blocking assignment operator out, right? Okay, so let's try this and see what we get. So vlog top.sv, and we'll go back and take a look. Restart. Okay. Okay, now you'll notice the out val. Oh, that's interesting. Let's see, are we still getting, okay, so the out val in this case, yeah, so you can see it looks different. So what's happening now is when you get a rising edge of the clock is when you do a write, right? Now, one of the things I wanted to point out here, but it's a little hard because we're always writing AB in. Let me change that. Let's put another value into the RAM. Let's see, what should we write? Let's see here. Let's write C. I wonder if that will make a difference. Vlog top.sv. All right. Restart. Okay. And radix hex. Yeah, it's still writing AB. That is
Maybe you should restart your simulation.
yeah. Well, I did. I restarted it. I have been restarting, but you know what? I'll restart all the model sim just to be sure. Normally, you don't have to do that. fact, I'm also going to remove the work directory, and then I'm going to vlog top, okay, and then we'll vsim top. We rerun that. So as I mentioned, work is the directory. Every time you vlog anything, it goes into the work directory in whatever directory you compiled it in. So if you compile it in one directory and you try to run it in another directory, it may say it can't find your design. So just be aware of that. Okay, and again, I'm going to do a right click here and add wave. And that's going to add all of the signals except for the RAM. So I'll go ahead and just, I'm going to go ahead and run this right now. Run. And, oh, there we go. Now it's fine. Weird. Okay, so let's convert this to radix hexadecimal. And you'll see I'm getting different values now out of outval. I don't know why I was getting A, B there for a while. Now you'll notice I don't have the RAM anymore, so I have to add that. As I mentioned, you have to, for whatever reason, ModelSim requires you to add the RAM manually. So we'll go over here. Now you'll say, well, you also notice now there's no data there, right? But if I continue running it, the data will show up from the point I added it to, like from the point at which I added it, because ModelSim doesn't record the state of every signal, only the ones that you've plotted. So I'll go ahead and expand out the RAM, and I'm going to convert this guy back out to hexadecimal. Radix hex. And there we go. You can see that there's different values in there now. It's so weird. I've never seen that happen before. Okay, so I'm going to zoom in here, and on ModelSim, I'm also going to zoom in on the screen so you can read that. Let's see. Let's click out. There we go. Okay. Okay, so we have a rising clock edge there, and that's where we're going to get it right. And the value we were writing, the address is, what address would it be writing to? Is it still A, right? Yeah, so to 0. And so the value that it's writing is, to 1. 1? Yes, sorry, 1. So the value it's going to be writing is 1. Now this can be confusing too, because notice how on the rising edge, so I've put my cursor here on the rising edge of the clock, and you'll see that, wait a minute, A, which is the address, as well as the value, am I writing, I think I would change it to C now, yeah. So A is the address, or at least the low order 4 bits of A is the address, and C is the data, but both of those are changing on the rising edge of the clock, right? So I'm writing on the rising edge of the clock, and they're also changing on the rising edge of the clock. So how do I know what I'm writing? Well, you're going to use, in this case, because I've used non-blocking assignments, it's going to be taking the value before the change, right? So the address should be 1, and the data should be 5, right? So address is 1, which is down here, and the data is 5. And oddly, the data was already 5 in there, so that was a bad example. So let's take a look at another one where it actually changed the entry. Okay, so on this rising edge, I'm going to be writing to address 0, and I'm going to be writing 82. And boom, you'll see it changed to 82 right there. Okay? Okay, now outval, notice that outval is also 82. Okay, now but this one is a little weird, because A, the low order 4 bits of A didn't change. It was A0 and then 50, right? So the address on A stayed at 0, which this was a great example because you can see that when I wrote 82 to A, the outval updated to 82 right away because it's asynchronous, right? Now, if I had the read inside of the clock logic, I wouldn't have seen the 82. I would have still been seeing the old value that was stored in address 0. I would have still been seeing 41 there. Does that make sense? I've got a better example of this on the slide I can show you. Whoop. Yeah. So this is outside, right? So the read happened right away. Now this is a hard way to show synchronous versus asynchronous because both the read and the write have the same address, right? But I have another example in the slides here where that's not the case. Okay, so yeah, sorry. This really quick. Let me just go show you this real quick here. So here's an 8192 by 32 RAM. This has an asynchronous read. So the number of bits is going to be the log base 2 of 8192, which is 13 bits. So the address is 12 down to 0. And you'll notice that the reason it's asynchronous is because of this assign line. So I assign the read data outside of the clocked logic. So anything inside this always is going to be clocked or synchronous, right? So this is essentially the same thing I showed you before because in this case I'm still have one address. I'm reading and writing to the same address. Now it doesn't have to be the same. And this would be the synchronous version. The only difference is I moved the read line inside the always. Okay, so I guess I did use the same address for both of these, didn't I? Yeah, okay, so that's okay. So I think the other difference here, though, is that I have a write enable. So I didn't have a write enable in the example I showed you. I assume it was on this slide, right? Yes, yeah, so it's in the slide. So there's this if write enable that's part of the write line, the line of code that does the write. You might say, how do you know that does the write? Well, it's just because the memory is on the left-hand side of the assignment, so that's the write line. And it's prefaced by if write enable. So there's a write enable there, so it'll only, now your register file has to have that too because not all instructions write a register. Most of them do, but not all. Like branch instructions don't. Okay, so in this case, I've got the address is incrementing 4, 5, 6, okay, but once it gets to 6, it stays at 6. Okay, so the data I'm writing is dead beef, and so I want to write dead beef into address 6, right? Write enable is 1, right? Now, when is that write going to happen? Well, it's not going to happen until the first rising edge of the clock, right? After 6 has been established is the address. Okay, so in other words, I'm going to be writing on this, I'm going to write dead beef to address 6 on this rising edge, right? You guys with me? Why is that? Why not this rising edge? Because this rising edge was actually going to 5 because that's what 5 was before the rising edge, right? So this is why things are a little confusing when you're writing at the same time you've got changing address and data, right? Okay, so in this case, I write to address 6, I hold the address 6 there, and notice how dead beef gets spit out right away, right? Whereas over here, there's a delay for 1 cycle. So because of that, this is the asynchronous version on the top, and this is the synchronous read version on the bottom. You guys with me? So let me clarify that. When you write, it's always synchronous. You always use the clock to write, but reading can be on the clock or instantly, right? Asynchronous read is an instant read. So you're going to use asynchronous reading on your register file because you want to be able to read the registers and do other stuff with those register values in the same cycle. You guys with me?
I have a question.
Yes.
If this is synchronous, why we have this read data tightened to the clock? Why it don't show up asynchronously out of the clock?
The data?
Yeah.
Well, because it just so happens that it doesn't depend on the clock, to answer your question, but it does here just because the address depends on the clock, right? Or the address changed on the clock. Not necessarily depends on it, but it changed on the clock edge, right? So in other words, so to answer your question a little better, I think, is if I had changed the address a bunch of times up here outside of the clock, then you'd see a corresponding change on the data coming out, right? Now, the problem is you don't generally see that because all the data paths are operating on the clock, right? But if I could reach in, with my hands and I can manipulate the address inside of a clock, then on an asynchronous read, you'll see the data be changed with the address at the same time the address does, right?
And we are writing rising age or falling age of the clock, write data right into the memory, which age?
What's that? I'm sorry?
Write data,
Mhm.
which age of the clock it is writing into the memory.
On the rising edge.
The rising.
Yes.
So when we have this 06 address and have rising age just before the dead beef appears. No, on the top. Here.
Yep.
Right. So, like rising age of the clock when dead beef appears on the data. Next.
Over here, on this edge.
Yes.
Okay, yeah, so the write data is 0, so what did I write here? I wrote to address 5, I wrote 0 to address 5 on that edge.
Well,
Because I had 0 here, and I had 5 here, and those are the values just prior to the rising edge.
but we have write enable 0 at that point.
Oh, yes, that's a good point. Yeah, you're right. So you're right, it actually wouldn't have wrote because of write enable. I wasn't looking at that, you're right.
Yeah, so it writes next rising clock.
That's right. Yeah. That's write enable. That rule also applies to write enable. So because you're right, write enable was low, so it would not have written.
Yeah.
So you're right. Yeah, I forgot to check that. Okay. So this is the register file that we're going to give you. The register file. We used to have a lab for this, but it's not big enough to justify a whole lab. So we're just going to give you the register file. So the register file is the same one that you guys studied in 212. It has 3 ports on it. So there's a read address 1, read address 2, with their own corresponding read data 1 and read data 2, right? So this is meant to match up with the RISC-V instruction fields RS1, RS2. So the instruction comes in and you take the 2 5-bit fields and you treat them like addresses for this RAM and you stick them in to these 2 address ports and the corresponding values of those registers will be spit out. Then there's a write port with write address and write data, and those are meant to line up with the register RD field, register destination gets plugged into that, and the write data is going to come from somewhere, depending on where you want to get the data to write. Yes?
Once again, why we have 2 reads? To read address and to read data. One is sufficient. Like 1 read address and 1 read data. Why we have 2?
So the 2 read addresses, so these are ports. So we want to be able to read 2 values out of the RAM in parallel. And we want to write one in parallel at the same time. So we want to do, so I haven't showed you this yet. I'm going to show, the code is right here. But in the example that all the examples I showed you so far, I only had 1 port, right? Actually, that's not true. Actually, the one I wrote up and demoed for you had 2 ports because technically, although there was only 1 address, so I guess it was 1 port. I could do a read and a write, but yeah, there was 1 port. But here I have 3 addresses. There's 1 port per address, so I can do 1 operation per address on the same shared memory, right? So this is like a shared RAM with respect to the ports, right? So I can read 2 things and write 1 thing, all in the same space, memory space, right? So for every address port, or so for every address input, I have a port, right? So in this case, I'm reading 2 values, writing 1 value. Although I don't have to write a value because I have write enable, I can disable the writing functionality, but it will always be reading 2 values. Yes?
Can it simultaneously read and write to the same address?
Yes. So that's a good question. So what happens when you do that? It depends on the code, right? So in the case of the MIPS and RISC-V CPUs, they have this behavior called forwarding where if you read and write to the same address at the same time, you want to make sure that the value that's spit out on the read is the value that's currently being written, right? Make sense? So you don't want the old value to come out. You want the new value to come out. So that's the reason why the code is written this way. So you'll notice that this is, first of all, this is all in a module called reg file 32 by 32. There's a clock input. There's the 3 addresses that are all 5 bits, right? And then there's an output for read data 1, read data 2, and then another input for write data 1, which is the 32 bits. And then we declare the memory. We just call it mem. This is the same way I showed you how to declare that. Now, this is where things get a little weird, though. As for writing is pretty standard. Just always FF, pause edge clock. If write enable, then you take write data and you put it into the memory at write address, right? So this part is the same way I showed you how to do it. Now these 2 assign statements are asynchronous reads, but you'll notice that there's this ternary operator. Okay, so there's basically for each read port, and this is basically copy and pasted code. These 2 statements are the same, except one's for 1 and the other one's for 2. You'll notice that there's 3 ways to read. If the read address is 0, then I want to spit out 0 regardless of what's in the memory. So I'm gonna just always put out a value of 0 if you read address 0, because in both RISC and MIPS, RISC-V and in MIPS, register 0 is always 0, right? Is always read as 0. If the read address is equal to the write address and the write enable is asserted, this is where I have this forwarding path where I want to say, okay, I've got, I might not have actually written yet, but I know that at this moment in time, I'm trying to write and read from the same address on port 1. So I'm going to just go ahead and take the write data and spit that out. Otherwise, I'm just going to send the contents of the memory, right? Now notice that I've got, the reason I have 3 ports is because I reference memory in both of these assign statements. This is happening concurrently. So these are 2 parallel concurrent statements. So I can do these 2 reads at the same time, and they're essentially independent of each other. They share the same memory though, because I use the same name. And then this guy is the write port, and he's the 3rd port, the 3rd access point into this memory, right? And so this is the register. The register file is 3 ports. It's kind of unusual to have 3 ports. It's complex to design a 3-ported memory, and that's why the register file is so small. It's only 32 registers. Okay. Okay. Yeah. So that's basically it. There'll also be an instruction memory that will be read-only that you'll use, and it'll just have 1 read port, but it'll be set up the same way, similar way, except synchronous reads. Okay. Okay, so that's takes care of the memory. Let's talk about the ALU. So we're going to give you the ALU as well. We're going to give you the code for this, so you don't have to worry about writing it. Which actually it makes sense, because when you do hardware design, it's very common to pull in IP, like pre-made blocks from other people design for you, and pull them into your design, right? So you can think of it as like an IP library that you're using. So the ALU is very simple. It's combinational logic, meaning there's no clock, and it just has 2 32-bit inputs and 1 32-bit output for A, B, and R, in which you're doing essentially an arithmetic or comparison or shift operation on these 2 inputs and producing a single output. And then there's an op, a coded operation code, which tells the ALU which operation to do, which is 4 bits. And then there's a 0 flag, a single bit output called 0, which is true or false, depending on whether R is 0 or non-zero. Okay, and we're going to be using that for branch decisions when we implement branches. But for lab 3, you're going to just ignore it. Okay. Okay, so there are 16 possible operations because there's a 4-bit opcode, but we don't use all the codes. We only have, I think, 12 actual unique operations in there. Okay, so we essentially just have 1 operation for each of the RISC instructions we're going to implement. Pretty simple. We've got AND, OR, XOR, add, subtract. Then there's the 3 multiplies that I described. Yes?
Operations 10 and 11 are the same?
Yes. Yeah, some of them are the same because we don't have 16 unique. So So some of these inputs are don't cares, essentially. So A times B, this first multiply is going to give you the low 32 bits, the low order 32 bits of the product. And these other two are going to give you the high order 32 bits. And then there's one for signed and unsigned. Okay, so in other words, when you do a multiply, if you only look at the low order 32 bits of the product, it doesn't matter if it's signed or unsigned. But it does matter for the upper 32 bits of the product. And then we have shift left logical, shift right logical, shift right arithmetic. And I talked about those when I was going through the RISC instructions. And then there's a less than B, set less than, signed and unsigned. Okay, so this table also appears in the lab description, and you can also get it from the slides, and you can read it right out of the code. And if you look at the code, it looks like this. I'm sorry it's so small. But basically, this is the ALU code, and we've cleaned this up quite a bit to try to make it easy to read. But basically, you can see how it works. We have some assigns over here that pre-calculate the multiplies. And then this block of code is actually kind of a hack that we put in because for some reason, I don't know if this is still the case, but when we did this last semester, ModelSim wasn't performing the right arithmetic shift correctly based on just using the greater than. So this code is little block of code that just performs the behavior of a right arithmetic shift. So it's a right shift, and it shifts in the sign bit. Yes.
Yeah, I remember this one when Charles and I were testing out the ALU design. We found that the old versions of ModelSim had a bug where you could not get right shift arithmetic. It always gave you right shift logical. So it was just shuffling bits around as opposed to doing the sign extension. And there was no way to work around that bug other than making custom Verilog logic to get around it at the time. If we're using a newer version of ModelSim, they may have fixed that because that was a silly bug. But for now, we just left that in because it works. It's a little janky, but it'll be efficient when it's synthesized. Yeah,
you'll notice that ModelSim assumes that all of these logic signals are unsigned by default. So if you want to do a signed operation as we do with the multiply here, or as we do over here with this set less than signed, you have to use this typecast, this little signed function. Okay, so now let's talk more about Lab 3. So Lab 3, I forgot to recount those. Is there 22? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Yeah, 22. There's 22 instructions that we want you to support in your initial version of the CPU. So you might be thinking, like, you can kind of see where the jump in difficulty is here now, because we're essentially asking you to build an entire CPU in one lab that performs these instructions. But keep in mind that most of these instructions are very similar, right? For example, the difference between an add and a subtract, they're very similar in terms of the data path and what happens. The only difference is what code you send to the ALU, right? But everything else is the same. You read two registers, you shove them into the ALU, you tell the ALU to do something, add or subtract, take the result out, you put it in the register file, and you write it according to the register destination, and then you go and fetch the next instruction. And the same thing is true for multiply high unsigned, set less than unsigned, and or XOR, and then like the immediate versions are also very similar, except they're taking the immediate value as the input instead of the second contents of the second register. Yes.
Can you use it? For example, if you implemented AND and then you implemented subtract, you can just flip the sign of the number you are subtracting and then use what you made for add.
Yes. Yeah. As a matter of fact, that's a good point. So the question is, do we even need all these instructions? We don't. We could build a CPU that's Turing complete that can run any program with actually a much smaller set of instructions if we wanted to. because some of these can be built with other things. Likewise, like for example, like the shifts, for instance, right? There's a shift and there's a shift immediate. The regular shift uses a variable shift amount, but you could, for example, just have an immediate shift that shifts by 1 bit and put it into a loop, that loops and shifts the appropriate number of times. So you don't need all these. We chose these instructions. We just hand-picked these essentially by looking at what the most popular instruction or the most common instructions are that are generated by a compiler. And so I think with just these instructions, and of course the branches and jumps, which we'll add in the next lab, even with that small instruction set, you can actually execute programs that are compiled with a C compiler in most cases. Sometimes you'll get a different instruction out, right, that you don't support. But we tried to support all the common ones generated by the compiler so you could compile code and run it on your CPU. Yes?
This is kind of a RISC question, but if you wanted to shift left 1 bit, but the bit is 1, would you have to use a shift left immediate or shift left?
If you wanted to shift by 1?
Shift by 1, but shift a 1 into that place.
Oh, in other words, I see what you're saying. You want to shift an immediate. Yes, good question. Yeah, in order to do that, you need 2 instructions because you'd have to preload a register with the value of 1 that you want, the constant value of 1 that you want to shift. And so, no, shift left immediate makes the shift amount a constant and immediate, not the value you're shifting. Now, one of the things that really sucks is the branch. The branch instructions don't have an immediate form. So, a lot of times you want to say branch of less than 5. Can't do it. You got to load 5 into a register first, and then you got to compare against that register, and then it takes up a register, and you potentially clobber a register that you were using. So that's the real pain, the branch ones. There's no way to just shove an immediate inside the comparisons. But no, yeah, you need 2 instructions. Now you might say, wait a second, I don't see a load immediate in there. How do you do a load immediate? Well, you actually just do an OR immediate with register 0, right? And the load immediate is a pseudo instruction that will be translated into OR immediate. So we do have load immediate. Okay, so now this is different. This is different than the instruction encodings are different from MIPS that you learned in 212. So this will be new for you. There are at least 6 different ways to encode instructions in RISC-V. There was only 3, remember, in MIPS, right? So for this lab, we actually need 3 for this lab, and we'll be adding 2 more in the next lab. So we've got the R type and the I type, which are very similar to the MIPS versions, but then we have the U type, which there was nothing like this in MIPS. So the R type is for register instructions, and so all of these guys are the R type, and so there's 2, 4, 6. There's 14 instructions that fall into the R type category, and the R type category is pretty much just 2 operands and 1 destination register, right? RS1, RS2 are your input registers. RD is your output register, right? Now, the thing I personally hate about this drives me nuts, is that there are 1, 2, 3 opcodes. There's funct7, funct3, and opcode. So the control information, in order to decipher what instruction you have, is coming from 3 different places scattered throughout the instruction. Which is very inconvenient. Charles came up with an idea to deal with this in the hardware, where you can actually, instead of just making, like what we used to do in this class, is we'd have the instruction and we'd feed it into a control unit, and it would look up table. It splits out all the control signals. The problem is when you design the control unit, you have to deal with these fields, which get kind of complicated. So Charles came up with this idea, which I thought was good, which is he has you can create a separate instruction decoder module, which essentially just renames each of the fields appropriately. So you can have like a little assign statement that just says func7 equals instruction 31 down to 25, right? That's the most significant 7 bits. And then you've got func3 is 14 down to 12, okay? Now where it gets weird is that you go to the I type, and the I type has, it has the func3, but it doesn't have the func7 because the func7 and the second operand register were replaced by a 12-bit immediate. Now remember, MIPS had 16-bit immediate. So there's a 12-bit immediate. Yes?
What are func3 and func7?
So they're little control codes that allow you to distinguish between different instructions. Now remember, in 212, it was a little easier because all R-type instructions had a 0 opcode. And then you would rely just on the function code to figure out what instruction it was, right? In RISC, that is not true. There's no convenient pattern like that, where all R-types have a 0 opcode. No, if I want to figure out what R-type instruction this is, I have to read all 3 of those fields, the func7, the func3, and the opcode, and together, I can figure out what the instruction is. So that's what they're little ways to discriminate the individual instructions. They're put in there by the assembler, right? So when you go from assembly to machine language, those bits are set. Okay, so the I type has the func3 and the opcode, but it obviously doesn't have the func7. Now you can still, as noted in the instruction, if you read that instruction, the lab sheet. The lab sheet tells you that if you build that instruction decoder, it's okay if you have a signal called func7 and you have an I-type come in. You might say, well, I can't, how can I decode func7 for an I-type? It doesn't exist. That's fine. You just will ignore it in your logic, right? Okay, so basically, you'll have these fields that you can have the immediate field or immediate 12 field and the func7, and they're both technically sharing bits, but they're 2 different, signal names inside your Verilog. Okay? And then the U-type is only for the load upper immediate, and that has a 20-bit immediate. Now you can pretty much see what's going on here. The reason why the LUI has a 20-bit immediate is because it's designed to complement the 12-bit immediate in here. So if you want to load all 32 bits for a register with a constant, you have to use a load upper immediate to get the upper 20 bits, followed by an OR-I instruction that'll give you the last 12 bits, right? Now remember, in MIPS, it was 16. Everything was 16-bit. The load upper immediate had a 16-bit immediate, and the OR-I had a 16-bit immediate. But now it's not evenly, chopped in half like that. Okay, so for the I-type, we've got 7 instructions. You'll notice there's no, in MIPS we had a NOR instruction. There's no NOR instruction. I don't know what the RISC-V guys have against NOR, but they took that out. But there's an OR-I, there's an XOR-I, and there's an AND-I. There's no, the other thing they took out, remember I was complaining about the comparison stuff, right? Comparing to an immediate. There's no set less than immediate. They had that in MIPS. They don't have it in RISC-V. They got rid of that too. So you have to preload a register if you want to compare anything to a constant. You got to preload it. I don't like it, but the good news for you guys is that it simplifies the hardware because you don't have to implement that instruction, right? So we have less instructions now with RISC-V. Okay, any questions about that? So all of these instructions are described in the lab sheet, as well as the their behavior, as well as their encoding, as well as all of the fields. One thing you guys might have been used to in the MIPS version of the 212 material, there was a reference card in there. You remember in the beginning of the textbook? That reference card had all of the opcodes in it and function codes. The new reference card for RISC-V doesn't have those, at least not the one that we've got on Dropbox. So unfortunately, your only source for those codes is going to come from the lab sheet we give you. I don't have any other thing. That's the only place you can get those codes. I mean, you can get them online if you go to the RISC-V spec, but in terms of what we give you, the only thing we give you with these codes is the lab sheet. That's why their lab sheet's so long. I got some feedback last fall from students who they were annoyed that the lab sheets were so long. I said, you expect us to read a 19-page lab sheet? But most of it is reference material. Okay, all right, so let's talk a little bit about the CPU, the top level design. So the way this will work is, and this, by the way, this isn't necessarily how you're going to subdivide your modules. This is just conceptual, right? Yeah. Essentially, you're going to have the FPGA, and inside the FPGA, you're going to have a CPU. You're going to have a 32-bit RAM that will serve as the instruction memory. Okay, so that's where your program will go, your code, your software goes in there, and then you're going to have your 7-segment decoders, and that's it. So all of the program memory will be on chip, so you don't have to worry about going off chip to DRAM. You don't have to worry about caches, because all of the RAM for this CPU is going to be on chip inside the FPGA. There's also, we're not doing load and store instructions, so there's no data memory. You might notice there's a big missing. We used to do load and stores, and that's where we used to put the data memory right there, but I took it out. Simplify things here. And then you're going to put your decoders in there. So we're going to have a key 0 is the reset, switches are the input, switches from the board, and then the output is the hex 7 through hex 0. So there's 56 bits coming out here because there's 7 bits per hex digit, and there's 8 of them. So 56 bits coming out, and then there's the switches, what was it, 18? 18 bits coming in for the switches, and 1 bit for that key is the reset, and of course the clock. So this is the top level design. We just have the 3 inputs and the 1 output. All right, so you're going to load your instruction memory, and then this will allow your CPU to do anything that's possibly computable, given these constraints. The switches as inputs and the hexes as outputs, right? So in the first lab, in the lab 3, we're going to ask you to write code that will convert binary to decimal. And then in the next lab, we're going to ask you to do the square root. So you'll bring your square root code in. So you'll put in, you'll reuse your square root code. The user will flip the switches to produce an 18-bit integer, non-fractional, just integer value. And then your CPU will calculate the square root, which of course will be a fractional number, and will output that onto the hex displays as a fractional decimal number containing 3 digits, decimal point, 5 digits. Okay, so that's why we had you write that square root code, and so you'll basically have a fully working, like sort of a tangible square root calculator that you can physically use, for which you design the hardware and the software. Okay, okay, so yes.
I have a question to the previous slide.
Yes.
Here we will have like 77 until 7, like hex 0 to hex 7. It's 8, so we have 8 decimal numbers of the quarters, but there is only, I believe. Oh,
No, there's 8.
8.
There's 8, yeah. That's the whole reason, by the way, we use those boards, because they're the only boards that have 8. Every other board you buy has either less than 8 or 0, right? That's why we're.
Display, you could use display.
Yeah, there's an LCD display. Yeah, it's a little bit more complex. So we could use that, but it would require more coding. You'd have to write more software, and this is a hardware course, so I don't want you to have to write a lot of software. Yep. Okay, okay, so now you guys remember there's from your. Now, if you haven't guessed, just to be clear, right? RISC-V is a knockoff of MIPS, right? Essentially, right? It's just they changed they made the smallest number of changes so they wouldn't get sued, right? So the stuff you learn in 212 about designing the CPU and MIPS, all of that stuff applies. In fact, like I said earlier, the hardware design for RISC is actually a little simpler because some of the complexities that MIPS introduced by having different registered destination fields for I-type and R-type, and having like I mentioned, this set less than immediate instructions and stuff, that's gone. So the hardware is actually a little simpler. But you probably remember there was 5 stages of execution in MIPS. there was fetch, decode, execute, memory, and write back, right? And if you're doing this all in one cycle, you have to do all of those steps in one cycle, right? Or you could do it as a multi-cycle CPU, where it could take between 3 and 5 cycles, depending on the instruction. Or you could do it as a pipeline CPU, where you perform all 5 stages in parallel at the same time, right? In this class, we didn't want to do a 5-stage pipeline. So we want to simplify a little bit. We're going to do a 3-stage pipeline. So we're going to combine the 3 middle steps, decode, execute, and memory, are going to be combined into one stage. And in fact, I mentioned there's no load and store instruction, so really there is no memory step, so you can kind of forget about that. So we're going to have fetch in one cycle, and while we're fetching an instruction, we're going to be decoding and executing the previous instruction, right? And we're going to be writing back the instruction that was 2 instructions ago, right, into the past, right? So we're always going to have 3 instructions in progress, but we're going to overlap their execution. So there's going to be 3 instructions being executed at one time, but only 1 instruction will finish every cycle. So ideally, once the pipeline is filled, we're executing 1 instruction per cycle, but we're always executing 3 instructions at a time in the pipeline. Okay, now, why did we do it this way? The reason is because the instruction memory is a RAM, and I mentioned that most larger RAMs have a synchronous, this all comes back to the synchronous read versus asynchronous read. Larger RAMs are going to have a synchronous read. The only asynchronous RAMs are register files, essentially, right? So when we fetch an instruction, we got to give it a whole cycle. If you want to fetch an instruction, you got to wait till the next cycle before you're going to get it, because the instruction memory is going to be synchronous. Okay? So that's why we have to separate the instruction fetch as its own cycle. And then, likewise, when we had the memory stage in there, of course, we had the memory stage as the second cycle. But even now, you might say, well, you don't have the memory. Do you really have to make execute and write back separate stages? Well, yes, because by doing that, we increase the clock rate, right? So we're going to make the execute its own, the decode and execute. So reading the registers and performing the ALU op, that happens in one cycle, and then the write back happens in the next cycle. Okay? Now, could we combine these all into one cycle? Yeah, but it would be a slower clock rate. The clock period would have to be longer. Okay, so if we did everything in one cycle, it would be like this, right? If we had 3 instructions, a gray instruction, a teal instruction, and a purple instruction, everything for each instruction would happen in one cycle. But with a pipeline 3-stage pipeline, it takes 3 cycles of latency to get an instruction through, right? But we overlap these guys, and so we're still doing 1 instruction per cycle, but each instruction takes 3 cycles to get through the pipeline. And so our level of concurrency is 3, but our latency is 3, and our throughput is 1. Okay? You guys with me on that? So what does this mean in terms of your design? What is the implications of this? It means that your signals, when you're debugging your CPU in ModelSim, whenever you look at your signals, like you put your cursor down in ModelSim, you're actually looking at 3 different in-flight instructions. So it can get a little confusing, because you look at any signal you look at is going to be associated with one of 3 instructions. Now, how are you going to know? Well, we propose that the idea we came up with, it's probably how everyone does it in reality, but we just add a little suffix to every signal name that denotes what stage that signal is associated. Well, actually, it denotes what instruction that signal is associated with, right? So for example, we'll have PC, program counter, underscore fetch means that's the program counter value for the instruction being fetched. And then we'll have another signal called instruction underscore EX, which means that's associated with the instruction that's in the EX field. Yeah, sorry, EX stage, rather. Okay? Okay. All right, so let's, actually, I guess I'm just about out of time, so this is probably a good place to stop. So I encourage you to, we don't have lab this week, but if you want to work ahead a little bit, take a look at the lab sheet. It's long, but like I said, most of it is reference material, but there's a lot of tips in there on how to get started and how to test your CPU. And then next week, the TAs will help you actually get started designing. Okay? Okay, great. Have a great fall break.